Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome again to the new class of structural biology. Today we are starting a new module. This is on protein, and the first class we will discuss about amino acids and their properties. So amino acids, as the name suggests, have one amino group, an acid group, a hydrogen and a R group. They are the main building block in the protein, as we have discussed earlier. The structure of an amino acids, as I told now, is divided into few main parts. One, the N terminus, which is amino group, the carboxylic acid group in the C terminus, a hydrogen and a R group. Each amino acids are chemically unique from one another, and that happened because each of them have a different R group. Rest of the structure is same. All the amino acids may interchange between non-ionic and ionic form, as you have seen in the picture. So, as I told, there is a amino group, there is a carboxylic group, and then the R, you could have, as I showed earlier, a hydrogen which is glycine, CH3 group which is alanine, 2CH3 group which is valine, then a sulfur CH2SH which is cysteine, a CH2 aromatic ring which is phenylalanine, and they are called R. As you guys know mathematics, we call an unknown entity as X. Similarly, in amino acid, the unknown part of the amino acid which designate a unique amino acid is considered or denoted as R. So, an amino acid is a relatively small molecule with characteristic group of atoms that determine its chemical behavior. The R group is the only part that differs between the 20 amino acids. Let us look at what type of groups they are divided into. The first group is non-polar amino acids. In this group you will get glycine, alanine, valine, leucine, isoleucine, methionine, phenylalanine, tryptophan and proline. Among them, proline actually settle between the non-polar and the polar groups. We will discuss about that later. If you see, glycine have two hydrogens, so its R is hydrogen. Because it have two hydrogen, it is not chiral. If you remember, we talk about chirality in our last module. We will discuss about that in more detail. Alanine have a CH3, so it differs from glycine and it's chiral. So, among the 20 amino acids, 19 are chiral. Only glycine is a chiral. Valine have CH3 leucine have CH2 CH3 isoleucine have same structure as leucine, but the CH3 group shifted, CH3 CH2 CH3. Methionine have a sulfur group in it, but in spite of having that sulfur group, it is not polar because of the presence of a methyl group after the sulfur. Phenylalanine is having a aromatic ring, it is CH2PH. Tryptophan also have aromatic ring. There are one 6-membered ring followed by a 5-membered ring, and proline, very interesting, if you look at its alpha carbon as well as the amino group fixed in a ring structure, that is a new scenario. We are going next, but one thing I should tell here, amino acid chemistry and amino acid structures are extremely important for understanding the course. To understand biological macromolecules, especially protein, knowledge of those is very critical. Polar and hydrophilic, there are serine, threonine, cysteine, tyrosine, asparagine and glutamine. They are considered as polar amino acids, whereas aspartic acid and glutamic acid are acidic, whereas lysine, arginine, histidine are basic amino acids. So, who are polar, they have groups which could be ionized, but the ones which are acidic and basic, they have or they develop real charges. In our latter section of this module, we will see how those polarity or existence of real charge have helped those amino acids being in the protein doing non-covalent interactions. Non-covalent interactions are extremely critical part of something called protein folding. As from the beginning of this course I told, it is a journey from the protein sequence to protein function in between protein structure. What I mean is, when you see a protein sequence, you know about the covalent bonds, but the journey is about understanding these non-covalent bonds which are actually forming and breaking continuously and giving protein unique architecture. The goal of this course and the goal of biochemists, biophysicists, structural biologists to understand or to register those non-covalent interactions. Amino acids with acidic side chains and their derivatives, as I told already, aspartate and glutamate are acidic amino acids, whereas asparagine and glutamine, they have CONH, whereas acidic means COOH. So, this is aspartate glutamate, this is asparagine glutamine. Again, amino acids with basic side chains, there are lysine, lysine create one prong, one nitrogen, arginine have two prong, two nitrogen, histidine have its nitrogen inside the ring. So, it have two nitrogen, and it is very interesting which nitrogen actually shows activity. Sulfur containing amino acids, there are two sulfur containing amino acids, cysteine and methionine, whereas cysteine with its CH2SH is able to form disulfide bond. Methionine is unable to form disulfide bond because of the presence of poor Lewis acid, the methyl group. So, when there is oxidizing condition, two cysteine from the protein comes together and form disulfide bond. This is the only covalent bond which could form in physiological condition. All other making and breakings are comes into the non-covalent bond category. This is the only covalent bond, and as I explained, methionine cannot form disulfide bond. So, now we know about this 20 amino acids, but as we talked about our goal is to go for structure. This knowledge is not good enough. We will look back to the chemistry. I have already discussed about the position of those hydrogen, carbon, nitrogen, oxygen in the periodic table. We talked about that the atomic composition of living organism is more complex than others, but very interestingly, the biological macromolecules are formed with just small number of them. We talked about that they take hydrogen, they take carbon, nitrogen, oxygen. You see DNA, you see carbohydrate, you see lipid, and you see protein. You will see these 3 plus hydrogen, these 4, and then you will see in the periodic table there is phosphorus and there is sulfur. So, this is what our biology is mostly composed of. In case of protein, you already know that hydrogen, carbon, nitrogen, oxygen and sulfur is there. Sulfur is there in case of methionine and cysteine. Phosphorus is not there, but it is also coming as a post translational modification. What that means? Once the protein is synthesized and folded, there are enzymes who modify the enzymes. There are different type of post translational modifications. Among them, phosphorylation is very common, and phosphorylation have very critical roles in maintaining biological switching especially. There are other things like acetylation, sulfation, methylation, but phosphorylation is definitely something which have bigger role in controlling biology. Here if you see the electrons on outer cells, what we talked about in hydrogen it is in 1s, in carbon, nitrogen and oxygen it is in 2s2p, and we talked about the ground state and excited state, how they form the tetrahedral chemistry. So, the tetrahedral structure of carbon orbital has rigid steric strain which makes the basic building unit of the protein conformation. So, now we are talking about protein, but in the previous module I talked about how sp3 hybridization is important for carbon, but it is also present in nitrogen and oxygen, giving them CH4 methane for carbon, NH3 ammonia for nitrogen, H2O for oxygen. They are all hydrides and they have critical role in biology as well as they are relevant in discussing the chemistry where we are going for protein. So, if you consider organic compounds, they have carbon-carbon bonds, it is called catenation. Catenation is a property by which carbons could form any possible number of bonds. Popular example is fullerene. Because of their ability to catenate between themselves, carbon develop the biology. Carbon is developing the backbone of many popular polymers, and our discussion today is focused on protein, where also carbon take very critical role in developing the polymer. So, if atoms in a functional group have notable difference in electronegativity, then this functional group will express high polarity and will be highly active. What I am talking about? Carbon develop backbone, right? We agree to that. But consider a polymer which is having only carbon and probably hydrogen. Polyethylene, these guys develop very inert polymer, right? That's why plastic is so popular, because its inertness have helped us developing materials out of them. And now today, when we have already developed a huge amount of waste out of plastic, and the inertness which was advantage once, now coming as a disadvantage, because we are not being able to destroy them because of the inertness. So you understand, when there is a carbon polymer, carbon backbone, they have the inertness. Now in a functional molecule like protein, you cannot make it inert. So as in my language, you have to spice up the inertness of the polymer. How you could do that? You could do that by introducing positive and negative charge. So let us look at the electronegativity table. You will see that oxygen and nitrogen are way more electronegative, oxygen being the highest 3.5 and nitrogen is 3. Very interestingly, oxygen and nitrogen both could contribute the as negative charge provider. So what we need? We need a positive charge provider. So if I ask you who you think in the periodic table, look at the periodic table, it is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. I could go on and on, but you get these. You get lithium, beryllium, sodium, calcium, these as positive charge donor. Do you want to take them? A very clear and easy answer is no. Why? Because biology is very sensitive and we could not use anyone abrupt in biology. So we could not use metals as positive charge contributor in biology. So we cannot use those positive charge contributor. So what is the way out? Very interesting thing here. We have NH3 we talked about, right? Now if you remember, NH3, it's nitrogen, it's 1s2, 2s2, 2p3. So when it form sp3 hybridization, it have like this. Now when it form bonding with hydrogen, it fill up this. So this is covalent bonding. In addition, it could form coordinate bond. What that means? Now it could take another hydrogen, take the electron and share between two. So it would be forming NH4 plus. See, now we get the positive charge provider from in the form of nitrogen using a different chemistry. So here in protein we spice up using oxygen and nitrogen. If you remember, we have talked about the unique properties of water and how it used as a universal solvent, because if you remember it have two lone pairs. So, in the excited state we have excited state electronic configuration like this, and because of this lone pair repulsion, which is called Vesper effect, valence shell electron pair repulsion theory, the angle between the two hydrogen forming covalent bond with oxygen become 104 degree 45-50 minutes instead of 109 degree 28 minutes, which is in methane, the classic tetrahedral structure. Because of the angle being 104 degree 45 minutes, there is extensive hydrogen bonding. In addition, we get high polarity, high dielectric constant, hydrogen bond formation, which I told, and pH influence that makes water a universal solvent. But now we have oxygen, as I told, present in the acid part of the amino acid and nitrogen in the amino part of the amino acid. It have the lone pair and it have the ability to, so as lone pair contributor it is a negative charge provider, but then it form NH3 plus, so it is a positive charge provider. So, because of that nitrogen and oxygen are providing positive and negative charge, they are actually spicing up the amino acid, hence they are spicing up the protein. The functional module of protein, the way it would be performing the function is taken care by these groups being into different amino acids. Now, if you see when this chemistry works, as I talked about sp3 hybridization, so how it happened? Carbon in the ground state, carbon have 1s2, 2s2, 2p2. In the excited state, it have four unpaired electrons and forming 4 sp3 orbitals, which are giving a perfect tetrahedron and forming methane. Similarly, if you modify from methane, you will see that similarly it forms bond with another carbon, which form a bond with oxygen and a double bond with oxygen. So, here there is sp2 hybridization. So, the change of state of hybridization change the chemistry, and we know that it alter the bond length as well as the total constitutions. If you look at, this is a amino acid, the 3-dimensional structure. So, when you see, this looks very different, and by looking at the sequence you would have no idea how this double bond developed, how this single bond developed, how the R group with change of size, how it influence, right, all those things. So, I have taken an initiative where I want to revisit the amino acids. We have considered different atoms by considering a model. CSB means carbon single bond, C-res means carbon resonated chemistry, CDB means carbon double bond, OSB means oxygen single bond, ODB means oxygen double bond, NSB means nitrogen single bond, NDB means nitrogen double bond, HSB means hydrogen single bond, and SSB means sulfur single bond. Let us now come and consider the amino acids in a more close to structure way. So, if you look at this, this is glycine, this is alanine, this is valine, this is leucine, this is having an extra group. So, isoleucine, and this is methionine. Now, you see it is more clear how they look, how they take the void volume and all. Also, to help you, I tried to highlight the portion which is common to each and every amino acids. That would make your conception even clearer, that how they differentiate. I could have identify only the group where they differentiate, but I take a reverse approach. I highlight the common group. You see, in glycine you only get a hydrogen, in alanine you get a carbon with 3 which are hydrogen, so a CH3 group. Here they are single bonded. So, if you go back model where the carbon single bond is used, okay. Again in valine you see the CH2 CH3 whole 2 is there. In leucine you get CH2 CH CH3 whole 2. In isoleucine you get CH CH3 CH2 CH3. In methionine you get CH2 CH2 S CH3. So, now you see we are getting close to the structure, we are looking at the volume, because all the structures are now developed according to the apparent size. So, we make the balls according to how they are comparatively looking like. Same in polar amino acids, you see serine, you see threonine, you see cysteine, and you see proline. Remember, I told we will talk about proline once I put it on the non-polar group, and now I put it on the polar group. I will definitely talk about, but before that, when we are talking about serine and threonine, we cannot stop talking about tyrosine. So, if you now look at, you will see that again I am highlighting the common zone. So, you could find the extra zone like CH2OH for serine, CHOHCH3 for threonine, CH2SH for cysteine, CH2 with a phenyl ring followed by OH for tyrosine, and very interestingly, as I told, it is part of the ring in case of proline. So, why proline is being into both the groups in polar and non-polar? Because here the alpha carbon is locked, so the nitrogen could have shown the polar nature. Also, because it is locked, they actually, when a protein chain is going, in presence of proline, it always changes the direction. That is one reason proline is called helix breaker and it produces turns which are called rigid turn. When I am talking about turn and I am talking about rigid turn, I should also talk about glycine. You know glycine is the smallest. So, when it is there, it actually don't allow the helical packing. We will talk about alpha helix. You will see that the alpha helical development is because of C double bond ONH hydrogen bond which forms between N to N plus 4th residues. Glycine being extremely small again, it produces flexibility and presence of multiple glycine produce again a turn which is called a flexible turn. So, glycine and proline both have the ability to form turn, whereas proline because of its locked structure make a rigid turn, glycine because of its small size makes a flexible turn. Coming to serine, threonine and tyrosine, all of them have hydroxyl group CH2OH, CHOH CH3 and phenylalanine CH2OH. Because of the presence of hydroxyl group, they could make reactions. Most popular of them is phosphorylation. So, we talked about post-translational modification. Phosphorylation mainly happened to serine, threonine and tyrosine. Cysteine sulfur group is not crowded and it could form disulfide bond and in oxidizing condition, in reduced it make SH. So, because of the presence of disulfide bond, there are many motifs developed. We will discuss about those in later section. Acidic we have already talked about, aspartate and glutamate. Aspartate have its derivative asparagine, glutamate have its derivative glutamine. You see, when you consider acidic group, you see that they could use 2 prong for hydrogen bonding or salt bridge development. So, both aspartate and glutamate have the potential to do that. But when it comes to asparagine or glutamine, it is even more interesting. They could use as both donor and acceptor. And that is why when there is a nucleoside or DNA base, you will see that there is a asparagine or glutamine in the active site who are developing interaction with the adenosine, guanosine, thymine, cytosine. So, that is one of the very interesting property they have. They could switch their residues by rotating their rotamers, and by that way they could fit with many ligands. So, they provide flexibility towards ligand binding. You could also see how the group looks when you take the common binders. You will see CH2CO2H for aspartate, CH2CONH2 for asparagine, CH2CH2CO2H for glutamate, CH2CH2CONH2 for glutamine. A very interesting thing is glutamate with its optimum size could phosphomimic. What I mean by phosphomimic? If you have a serine CH2OH and it forms CH2OP through phosphorylation, if you could mutate the serine to glutamate, you will get kind of similar interaction if it being phosphorylated. So, a phosphorylated serine and a serine mutated glutamate behave similarly, and that is why now there are kits available, but in previous days used to use mutation of serine to glutamate as a strategy to phosphomimic. That is why glutamate is called a good phosphomimic to phosphorylated serine. Very interestingly, where glutamate used to do that, aspartate never did that. So, the size and charge both are important here. The basic amino acids we talked about there, lysine, arginine and histidine. If you now look at the elongation, lysine have a very big chain CH2, 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 NH2, and arginine have CH2, 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 NH, CH, double bond N, single bond NH2. So, it is a single prong, it is a double prong. Interestingly, in histidine, as I told, is in the ring. So, the nitrogens which one is going to bind is very interesting to find. Also, as I told, because of the big length, when they are specifically at the surface of the protein, they generally shows extreme flexibility, and when we perform X-ray crystallography, most of the time we cannot solve. When I say solve, I mean properly model arginine or lysine. So, what we do? We model it with the minimal size amino acid, which is glycine, right? No. We do it with alanine. Why? Because alanine is the smallest chiral amino acid. So, we want to model at least the chirality. So, when we could not be able to model lysine or arginine, we model it as alanine. So, sometime you see the structure and you find alanine in the structure, and in the sequence you find arginine or lysine, you do not panic. It is because there is a lot of disturbance, and that is why the crystallographer could not be able to model the arginine or lysine properly. So, he or she have modeled alanine. Aromatic amino acids, we will talk about them later in details, but they all have aromatic ring, whereas tryptophan having 2 ring have extended delocalization, and that is the reason tryptophan is used as intrinsic fluorophore. So, when you have a pure protein, without labeling it, you could perform fluorescence spectroscopy study of that protein if you have tryptophan in the protein. That is a advantage. You cannot use phenylalanine or tyrosine as a fluorescent marker, whereas you could use tryptophan as a marker. How you could use it? Let us say you have the protein and the tryptophan is inside. So, if you want to test how the protein is stable, what you could do, you have the protein and you have tryptophan in the core. You provide heat, the protein would be opening up and tryptophan would be getting access to the water. So, its fluorescence would be quenched. So, you could even measure the rate of folding if you are lucky enough to have one tryptophan inside the hydrophobic core of the protein. Also, you could set up assay of your ligand binding if your tryptophan is close to the active site or being affected by the ligand binding. So, that is why tryptophan helps you in studying. I was talking about the chemistry. I will discuss more when we are going to peptide bond's rigidity, its sp2 hybridization character, the partial double bond character. But one thing, you know, if you have to calculate the bond lengths with the changing chemistry, then it would be very difficult, right? Here is a method I will talk about now, which will give you a very easy measure of calculation of the bond lengths. How? See, remember I talked about carbon single bond, carbon resonated, carbon double bond, oxygen single bond double bond, nitrogen single bond double bond, hydrogen single bond and sulfur single bond. Here is a process, you see all of them have their covalent radius. Carbon single bond have 0.77, which is angstrom. Carbon resonated have 0.72 because of resonance, it reduced. Carbon double bond at 0.67 definitely reduced because of the development of the pi bond. Oxygen single bond is 0.67, oxygen being more electronegative than carbon, holding the electrons closer. Double bond is even lesser than single bond, 0.6, nitrogen single bond 0.7, nitrogen double bond 0.62, hydrogen single bond 0.37, sulfur single bond 1.04. What is the advantage? See here, you could calculate the bonds like NH, NC alpha, C alpha hydrogen, C alpha carbon, carbon oxygen, single bond, carbon oxygen, double bond, oxygen hydrogen, NC which is in the peptide bond, CONH, C alpha, CR side chain, all of them you could calculate, and we have just added them. We didn't do anything. So NH means N single bond and hydrogen single bond. So we take N single bond, which is 0.7 plus hydrogen single bond, which is 0.37, which means 1.07. So you understand. Similarly, nitrogen single bond is 0.7, carbon single bond is 0.77, so 1.47. So what we did, we have fixed the covalent radius of the single bond and double bonded elements which are involved in protein, and then added those to get the bond. So simple idea, carbon with carbon 0.77, 0.77, 1.54. Okay. And you will say, okay, you did it, how I believe that these are true? So here you see the red marked 1, 2, 3, 4, 5, 6 and 7. These are references starting from Pauling's Nature paper, where he first published the nature of chemical bond. We have taken very relevant references where people have calculated, and you see that the difference, the validity of that comes ranging from 0.06 to 00. So this is very accurate and you could use. So instead of understanding complex chemistry, you need to understand the chemistry, but for this calculation you could calculate the probable bond length with very easy calculation. If you understand this, you don't need to go into complex calculation. You just remember this 1, 2, 3, 4, 5, 6, 7, 8, 9 and you could calculate each and every bond in the protein. Easier? Follow this. Coming to physicochemical properties of different amino acids, you will see the chemical properties. We have already talked about leucine, non-polar aliphatic, lysine, positively charged basic, methionine, non-polar aliphatic, phenylalanine, aromatic, proline, non-polar aliphatic, serine, polar uncharged, threonine, polar uncharged, tryptophan, aromatic, tyrosine, aromatic, and valine, non-polar aliphatic. So in that way you could get the chemical properties. The molecular mass for leucine 131, you go back and calculate. That's a assignment from my side. More you do the calculation of the atomic compositions, more you understand the composition. Lysine 146 Dalton. By the way, the average molecular weight of amino acid is 110 Dalton. Methionine 149, phenylalanine 165, proline 115, serine 105, threonine 119, tryptophan 204, tyrosine 181, valine 117. Tryptophan is the amino acid with highest molecular mass. Number of atom for leucine 22, lysine 24, methionine 20, phenylalanine 23, proline 17, serine 14, threonine 17, tryptophan 27, tyrosine 24, valine 19, volume they are in angstrom cube. For leucine 166.7, lysine 168.6, methionine 162.9, phenylalanine 189.9, proline 112.7, serine 89, threonine 116.1, tryptophan 227.8, tyrosine 193.6, valine 140. As I told, tryptophan is the highest one. Hydropathy index is an important measure which gives you understanding which ones are more hydrophobic. Leucine 3.8, lysine minus 3.9 because lysine is charged, so negative hydropathy. Methionine 1.9, phenylalanine 2.8, proline minus 1.6, serine minus 0.8, threonine minus 0.7, tryptophan minus 0.9, tyrosine minus 1.3 and valine 4.2. Similarly, alanine is a non-polar aliphatic, arginine positively charged basic, asparagine polar uncharged, aspartic acid negatively charged acidic, cysteine polar uncharged, glutamine polar uncharged, glutamic acid negatively charged acidic, glycine non-polar aliphatic, histidine positively charged, isoleucine non-polar aliphatic. The molecular mass of alanine is 89, arginine 174, asparagine 132, aspartic acid 133, cysteine 121, glutamine 146, glutamic acid 147, glycine the smallest 75, histidine 155, isoleucine 131. You could also calculate by your own if you know the formula, like here you have this one common, then if you take glycine you calculate 12, so 12 plus 12, 2 oxygen 16 plus 16, 16, nitrogen 14, so 24 and 32 56 and 14 70 plus 1 and 3 5, which is 75. You see, this is 75. When you talk about alanine, a CH2 added, so C12 and 2 14, so it is 89. In this way you could calculate by your own. Also you could calculate the number of atoms. For alanine it is 13, for arginine it is 26, for asparagine it is 17, for aspartic acid it is 16, cysteine it is 14, glutamine it is 20, glutamic acid 19, glycine 10, histidine 20, isoleucine 22. For volume, alanine 88.6, arginine 173.4, asparagine 114.1, aspartic acid 111.1, cysteine 108.5, glutamine 143.8, glutamic acid 138.4, glycine 60.1, histidine 153.2, isoleucine 166.7, hydropathy index 1.8 for alanine, arginine minus 4.5 because its basic charge, asparagine minus 3.5, aspartic acid minus 3.5, cysteine 2.5, glutamine minus 3.5, glutamic acid minus 3.5, glycine minus 0.4, histidine minus 3.2, isoleucine 4.5. Among them, this is not surprising that glycine is the lowest molecular mass and volume. Also, histidine, I forget to say, is the physiological buffer. Coming to chirality, remember three things I talked about, the three secrets, the three C's of covalent bond. One is chirality, then configuration and conformation. So, chirality in amino acid is very important. Amino acids except for glycine have a chiral carbon atom adjacent to the carboxyl and amine groups. This chiral center allows the stereoisomerism, as there are 4 different chemical groups surrounding the carbon atom. We told already about that. It is a tetrahedral, it has 4 groups with a 109 degree 28 minute angle. With that you could put only 3 points together. So, carbon with its so you could either put, let us say A, B, D, E. So, you could put A, B, C, A, C, D in that way. Okay. So, one group have to, so if it is this plane, one group have to be above the and one group have to be below the plane. So, that is why which one is above the plane and which one is below the plane is called chirality. The amino acids with two stereoisomers are mirror images of each other and are called L amino acid and D amino acids respectively. The structures are not superimposable to each other, much like the left hand right hands. And if you see here, L amino acid and D amino acid, they are called stereoisomer. Glycine, both are same, whereas in alanine they are not same, and you see that it cannot be superimposable. Coming to the acid base behavior of amino acids exist as a deuterion, a dipolar ion having both a formal positive and formal negative charge. Remember, I talked about amino acid means carbon, NH2, CO2H, R group and hydrogen. Now, this could be COO minus and this could be NH3 plus. When they are both plus and minus, then it is charged. But interestingly, if you put it on a electrode, it is not going here or there, it is staying there. That stage is called deuterionic stage. So, as I told, you look at the pK and you see that how they are behaving. So, they are amphoteric, they can react as either an acid or a base. Ammonium ion act as an acid, carboxylate as base. What is isoelectric point or Pi? The pH at which the amino acid exists largely in a neutral deuterionic form, influenced by the nature of the side chain, the 20 side chains we have. So, when it is low pH, high amount of proton, it makes NH2, NH3 plus, whereas when it is high pH, it is more OH minus, it makes CO2H, CO2 minus. So, how that is different in different one? So, you could calculate the isoelectric points in such a way. For non-polar, you see that in low pH it is NH3 plus, then in high pH it is CO2 minus, in between it is deuterionic form. So, the Pi is pKx plus pKy. So, here it is 2.3 plus 9.7 by 2 is 6, whereas for acidic molecule which have a acid group, they become deuterionic at low pH and in high pH they are having 2 negative. So, here the Pi is calculated with pK1 and pK3 and you get 1.9 plus 3.6, which is 5.4 by 2 is 2.7. For basic who form positive ions at low pH, because 2NH2 becoming 2NH3 plus. So, the formula is pK2 plus pK3 by 2. So, 9 plus 10.5, which is 19.5 by 2 is 9.75. So, summary: at low pH proton concentration is high, therefore, both amines and carboxylic acids are protonated. At high pH proton concentration is low, therefore, both amines and carboxylic acid are deprotonated. At neutral pH amines are protonated and carboxylates are deprotonated, forming the deuterion, but that differs with the side chain, because if the side chain is having a amino group in low pH, it have more H plus becoming 1 NH3 plus from the amino acid itself, its amino group, the regular, and the extra amino group from the side chain, and reverse happen on the acidic amino acids glutamate and aspartate. They are having two negative charges at high pH. So, what I talked about, you could use this in separating the protein. So, separating amino acids as well as proteins. When amino acids will go into the protein, you will see that they are connected through the peptide bond. So, the regular amino and CO2H groups are not there, but the side chains are there and they will influence the pi. So, separation of polar compound based on their mobility through a solid support, the separation is based on charge or molecular mass. Generally, it is molecular mass, that is called SDS page, where we take a protein and we add negative charge. So, the protein is now bound by the negatively charged, which is the SDS, and then so the difference coming from the negative charge the protein have is not making much influence, because the added compound is very negatively charged. So, they bind. So, the proteins are nearly equivalent in terms of charge, they are separated only through their molecular mass. But then you could use charge and molecular mass, and that is called 2D electrophoresis. So, you could separate them in that way. So, we will talk about the levels of protein structures. We talked about this, that our goal is to go to the quaternary structure, journey from primary structure, which is the amino acid forming peptide bond, to the secondary structure, then different secondary structure comes together to tertiary structure, and tertiary structure is an independent chain. When multiple chains are coming together, they form assembled units or quaternary structure. I will finish here today. In the next class, we will follow up with the properties of protein identification and techniques which will help us to characterize protein, identify protein, as well as sequencing protein. Thank you very much.